All right.
It's high.
You may remember LeChatier's Principle. I was very actually happy to find that this year most people remember seeing this before, but you probably don't remember where. Let me explain to you using a little bit of what we did last year first, okay? LeChatier's Principle said this.
Wait, is it the PV equals nRT?
Well, we were using it right after that chapter about gases and liquids and solids. Basically, what we're doing, we're applying LeChatier's Principle to phase changes. Like liquid, remember doing this? Liquid plus energy yields vapor, okay? And so what I would ask you is, if I heat this guy up, or if I cool him down, am I going to favor evaporation or condensation? And good, you got out of your exit interview. All right.
Hey, I'm no longer playing at home.
All right, look at. Let me refresh your memory on this. Take a look. You may remember a little GIF I made here. It's an animated GIF. I put this together to try to illustrate what was going on. I used syringes, and we used the balance. Yep, got a good. We put a little thing on there.
You're on camera.
Actually, I'm off camera. Anyway, look at. So look, if I have a jar, it's got water in the bottom and the lid's on top. Eventually, as it sits there, evaporation and condensation rates will be equal. I'll have a little bit of vapor in there, and I'll have a lot of water, and some will be evaporating and some will be condensing, but they'll be happening at the same rate. That's an equilibrium problem, just like we've seen with chemicals. Okay, what happens if I increase the temperature of this guy?
There's going to be more evaporation.
Yeah, you're going to evaporate more. Absolutely, it's going to favor evaporation. So notice I made that arrow larger. It's evaporating more right now, and it's not condensing as much. So we end up getting more into the vapor phase. Because there's now more in the vapor phase, there's a greater chance of those guys banging into the liquid and becoming liquid again. So the condensation starts to creep up until eventually it reestablishes a new equilibrium, but look what's different. I now have more in the vapor phase than I had before, and I now have higher rates of both evaporation and condensation. That's one of the key things that people get wrong on these. If I told you that when I increase the temperature, when it reestablishes equilibrium, it's going to have more condensation, you would have said, no, it's going to have more evaporation. That's the initial effect, to have more evaporation, but eventually it does reestablish equilibrium at a higher rate of condensation as well. You'd also have to realize there's more in the vapor phase. Now, that was all last year, okay? And it was hard. It was one of the harder concepts getting right back then, and all you had to do was tell me one thing. Is it going to favor the forward, or is it going to favor the reverse? Now, you're going to have to do actual calculations with this stuff, okay, using LeChatier's principle. So let me show you how we're going to do it. But the basic principle has remained the same. He is Mr. Crew. Principle?
I think you used that wrong.
Yeah, I did. The basic principle has remained the same. And it says this. If I stress a system at equilibrium, the system acts to get rid of that stress. So if I heat them up, and I make too much vapor, it tries to get rid of that vapor by increasing the condensation. Increase the evaporation, increase the condensation. All right, it's going to always try to get back to equilibrium, however I stress the system. Now, I can illustrate that with a very simple example using ABC, calculate concentration in a reaction, but I'm going to also put it into words as well. This is going to be a very full class because we're only going to do one problem today, and it's going to take us pretty much the whole class. Matter of fact, I'm going to have to stop the video because the algebra does get very intense. Also, if you look at the homework over there, 64 and 65 of 748, there's only two problems, they're not ABCs. All right, they're basically, there's not a lot of homework here, but it would take you a period almost to do them. All right. Now let's take a look here. Here's my example. Okay, just watch this. If I have like A plus, don't copy this, yields C. A plus B yields C. Okay. In effect, here's what I'm saying. If I were to increase, if I were to add A to this container, which way is he going to go? He'll go forward, won't he? He'll try to get rid of the extra A I gave him. That's the stress. What if I were to take away B from this container? What would he do? He'd try to go reverse and replace B. What if I were to add C to this container? What would he do? Reverse to try to get rid of the extra C. And if I were to take C away, what would he try to do? Forward. Okay, that's in a nutshell what happens. That's the first step, but here's the problem. That's only the first step to try to determine which way he's going to go. Remember, over the course of the last couple of, I didn't mean to hit that. Over the course of the last couple of,
We didn't learn this.
What's this stuff?
Yeah. Technology.
Can't live without it.
Mm-hmm.
It's like one. It's like owl. It's like owl. Very good.
So, what have we been doing? We've been doing initial change in equilibrium. And we've pretty much always known which way it's going to go. You know, I would give you 0.2 of that and 0.2 of that and 0. I know which way it's going. It's going forward. If I gave you 0.2 of that and 0 and 0, I know which way it's going to go. It's going to go reverse. All right. But what I'm saying now is sometimes I'm going to add amounts to it and stress the system, and we're going to have to figure out which way it's going to go, stressing by adding A or B or C after it's already at equilibrium. And that's what we're going to be able to tell which way it's going to go again, using LeChatitelier's principle. It's going to go forward or reverse because I added A or removed B or whatever. All right, so here, in words, what I've just said. There are 4 ways I'm going to stress the system. Today's going to be the easiest one, and it's still going to take us the rest of the period to do the problem. We're going to talk about just concentration today. What?
So that's the easiest one. It's going to take us a little.
It's still going to take us a whole period. We're going to eventually talk about 4 ways. Concentration changes are the easiest to conceptually understand. We're also going to talk about, remember this from last year, volume and pressure changes. Pushing down on that plunger.
Yeah.
Pulling back on it. Temperature changes. Okay, we're going to talk about all of those different ways we can stress an equilibrium problem. But first of all, the easy one. Concentration changes. In effect, that one statement pretty much answers everything. However, for your own literal devices here, if you add a reactant or a product, the system is going to act to consume that reactant or product. Now notice what I said here. Notice how I said it. Because I know someone out there is hearing something that I didn't say. Okay? A lot of people think, and I know Lizzie's one of these people, like Shania, and I specifically said this to Shania, she still did it today anyway, and Lizzie will too. So if I add, it always goes forward. If I take away, it always goes reverse. No. The answer is no. Because what does it depend on? It depends on, look at how I've worded this. I never said that if I add something, it's going to go forward. I said if I add something, it will shift to consume that thing. So if I added C, which way is it going? Reverse. If I added B, which way is it going? Forward. You see? Second way to talk about it, you will mess this up, just saying. Second way to say, if I remove something, if a product is a reactant or a product is removed, what will it do? It will shift to do what? To replace it. It's going to try to get that stuff back. So just like I warned you about not trying to memorize what Q means, but rather understand it's forward over reverse and be able to predict, you're going to be doing that in 65 today. Well, not today, tomorrow. I'll give you some time to work on those. And again, I got the same questions. Well, how do you know? You're looking back at the notes. Okay, so if Q is smaller than KC, it goes this way. If Q is, just think about it. If you think about it, you'll understand it. All right. So those are just the literal, specific way the concentration will affect equilibrium. But really, this guy always is, you can apply to any situation. Temperature, volume, pressure, concentrations, any of those, you can apply that one statement to it, and it will work. All right, now it's time to do the actual math. Again, it was hard enough to figure this out when we just had to predict whether it was forward or reverse. Now we're going to have to do actual numbers.
Let's see. Right H.
Fun times here.
Not really.
No.
It's still hard to be a bio major.
Nah. I did. If I could do it, anybody could do it.
It's hard to be a chemistry major?
Why?
Harder to be a chemistry major. And even harder to be a physics and engineering major.
Oh, screw that.
You should be a chem major, but
I'm going to come back slide. If additional 3.00 molar HI is at.
So here I have a guy who's at equilibrium, and he tells me the equilibrium concentration. So that's easy. That's easy. And then
More cowbell.
I go and change it. I throw some more stuff in there. Okay? I got to figure out what's going to happen. Now, what I want you to do in setting this guy up, we are going to do the ICE eventually, but we're not going to start off with that. So leave yourself about 3 lines blank where you're going to put ICE. Okay? But we're not going to fill those in just yet. Let me tell you why. We're going to come back and do that. First thing I'm going to need, remember this actually has 2 parts to it. First question says, and I think in the homework it even says like A, calculate KC, and then B, if I do this, what happens? So calculating KC is necessary at first. How would I calculate KC for a guy like this? It's really pretty easy. What are you going to do? What's that? Yeah, and you're given them, right? You're just going to plug them in. So you need, and by the way, as I was doing this one, you're going to see, by the time I'm done, I'm going to need this part, so I'm going to cover it over here. Because I worked it out, the algebra over in this one, and I'll take this off later, but I want you all to work it out. By the time I'm done, we're going to have filled up completely 2 full boards, okay?
Is that really required?
It is.
Just to clarify something.
Yeah.
It gives you the molarity already.
Right. And if it said a size was a 4-liter container, and they give you mold, you have to divide it. Yeah. Now, secondly, listen to this. This is kind of important. I'm going to ask you to do the work the way I'm showing it to you here for a good reason. If I did, I said this, that's probably true. If I did 10 of these problems, I would probably make a mistake in 2 of them. Because there's just so much algebra and calculator numbers to plug in that you'd probably make a mistake. It'd be very hard to get through this entire problem, if you did 10 different ones like this with slight changes without making a dumb mistake somewhere. They're not going to cost you a lot of points if I can see where that dumb mistake is. If it's just plugging the wrong number into the calculator or a simple algebra mistake, it's not going to cost you as much as other ones. So here's what you need to show me. First, the equation. KC. You can't just go and throw those numbers in. You need to show me the formula. What's the formula for KC? HI squared over H2 times I2.
Yeah.
Okay? And then I plug my numbers in. So KC would equal HI squared. The reason you do this, it reminds you to square this guy. HI was 0.490 squared over H2, which was 0.080, times I2, which is 0.060.
Yay.
Do you get your calculator out? What does KC equal?
Oh, no, we can't.
Get the calculator. By the way, anybody who needs, you're going to need the graphing one soon and doesn't have one, come and get one. But you need to borrow one from your math teacher. Otherwise, you're going to not be able to do the homework. Anybody else need one? Don't bump the camera.
Why can't you use that one?
Because you can't take it home. And I don't have enough. I have 6. 1 died. All right. What'd you get for this?
Yeah, 0.018.
I don't think so.
Yeah, 50. I got
50. And you got exactly 50 because of significant figures, 50 decimal point. This guy only has 2. He only has 2. Did you remember to square? That could be a mistake.
Yeah, I squared it.
Okay.
I think I just did.
When you go this.
I missed the decimal spot.
Okay, that's a possibility, but if it's only a decimal, it should have been 5, a version of 5.
Well, I don't know what I did that.
Then it was probably something else. Look at
Yeah.
Let me show you. This squared divided by that, divided by that. You can't go this divided by this times that. You should know that. You have to use parentheses if you did that. So those are all different things you could do. But here's the nice part. Say, for example, you have this all shown, but you didn't get 50. You got both these answers, but it's shown like that. You've only lost 1 point. Okay? Whereas if you don't show me this all plugged in and you get the wrong answer, I have no idea where your mistake was. I don't know. You just hit a wrong number on the calculator. And so I have to take off more points. All right, good. We got KC. Now, let's take a look back to our problem here. Part 1 done. Part A is done. Second part. If an additional 0.3 moles of HI is added, determine the new concentrations. So your initial concentrations are not, normally they're like, 0.2, 0.2, and 0, or 0.2, 0, and 0. And you know which way it's going to go. Not this time. The initial concentrations are, for H2, it's 0.080. I didn't change him. For I2, it's 0.060. I didn't change him. But HI is 0.490 plus what? I added 0.3 moles of HI to that amount. So what is it? Add 0.3 to 0.49, what do you get? 0.790 molar. Those are no longer the equilibrium concentrations because I've added the 0.3 to them. They are your new initial concentrations, which are going to change over time. Now, LeChatelier's principle comes in right now. I could actually plug in for Q right now. If I plug those concentrations in for Q and solve for Q, and by the way, you'll have to do this on number 64, I think, or 65, one or the other. If I plug these in and solve for Q, it would tell me the same thing that common sense tells me. I added HI. A plus B yields C. Which way is this guy going to go if I added HI? Reverse, right? So I know it's going to go minus what? 2x plus x and plus x. Exactly. Now that's where the Chalets principle comes in. Is it always, again, some people are out there thinking so it's always going to be minus on this side and plus on that side. No. If I had added H2 or I2 or both, it would have gone that way because of common sense. But if you don't want to use common sense, you could always, and you have to, what if I added all three? What if I added some of this and some of that and some of that? Then what would you have to do? You'd have to give up. No, you would not give up. You would have to do what? You'd have to solve for Q. And if Q came out to be less than KC, it would mean I'd have to go forward. And if Q came out to be greater than KC, it would have to go reverse because it's KF over KR. Well, you can see what's going to happen here. Why this is even harder than the previous ones. Because now I've got a binomial everywhere. I've got a binomial everywhere. 0.060 minus x. I'm sorry, it's plus x. Plus x. And 0.790 minus 2x. Once again, I know you don't want to do this. I know I wrote it down once, so I have to write it down ever again on the test. Yes, you're solving for K. You're using the KC equation. Not solving for KC. Using the KC equation to solve for x. So I want to see the equation. KC equals HI squared over H2 times I2. I know what KC is. I said, well, why am I doing this again? The first time you did it, you were simply calculating KC. This time, you're going to use the KC you calculated to be able to figure out what the concentrations are in equilibrium. It's going to be 50. That's what you calculated KC to be. Equals H. By the way, 50 was correct for the units, too. You notice why I had no units? Because it was molar squared over molar squared, which is no units. All right, equals HI. HI concentration is 0.790 minus 2x what? Squared, that binomial. And then I've got another binomial down here, 0.080 plus x and 0.060 plus x. So I'm going to pause it so I don't have to waste time because it's going to take you a while. What do you now have to do? Let's just go through it real quickly before I pause it. You're going to have to square that binomial. You're going to have to FOIL that binomial. You're going to have to cross multiply, and you have to combine like terms. You're going to have to get your x squared all at the same positive function, all one side equal to 0. And that's what I want you to do while the camera's off. So let's take a look here. This was the equation I left off at when I stopped it a second ago. And that's what you had at this point. You had the KC equals this guy squared, this binomial squared over these two, which you have to FOIL. So I have it worked out here. Here's what you should have gotten. When you square that guy, you should have gotten that. When you FOIL these two, you should have gotten that. And then you have to cross multiply. Yeah, quick.
3.16.
3.16. I squared this guy. That's where I got it. It's going to be 0.790.
Yep.
And it's x times 2x, because if you think about it, use 2 times the first time the second, like I said, you could do that. Or if you were to just have another one up here, 0.790, first, outer, inner, last, right? Okay, outers and inners, adding those together. That's where you get the 3.16. Okay. All right, outers and inners. And then the square of the second one. All right, so this is what you should get. If you didn't, that's what I'm just showing it to you right now. Next step is to cross multiply. 50 times this guy distributing him is going to give you, all of these answers right here. This guy just cross multiplies the same numbers. Then I have to bring the x's. Squared function has to be positive. So I bring the 4x over to this side and make it minus 4x. It gives me minus 4x, it gives me 46x squared. And the other guys come over, they've changed their signs as well. And that's my equation. Now we're going to go back and move can you turn the lights opposite where they are? And we will look at where we left off here. All right. See how long these problems are.
How many are we going to have of this?
Only one like this. This sucks. Yeah. All right. So eventually, now what are you doing? I hope you already did it. You plug it into your quadratic formula program, and what did you get for your two roots? X equals what? 0.033 or negative. What is it? Well, whatever. It's a negative, so whatever it is no good, right? We know it's not right. So we use the 0.033. That's my x. Now, your final answer, what do you have to do with that? Plug him back in. HI will equal 0.790 minus 2 times 0.033. H2 is going to equal 0.080 plus 0.033. And I2 is going to equal 0.060 plus 0.033. Okay? And that will be your final answer for each of those, and you are done. Got it? That's a long problem.